Most people don't realize how peculiar it really is. We call it the speed of light, and we think of it as just another speed, like the speed of a car or an airplane. But it's not. It's something far more fundamental, and it's connected to the very nature of what we mean when we say now. And that's what I want to explore with you today. Let's start with a simple question. How fast does light travel? Well, we know it's approximately 186,000 miles per second, or about 300,000 kilometers per second. That's an enormous speed. But here's the thing that I find most fascinating, and this is where the mystery begins. This speed is the same for everybody. No matter who measures it, no matter how fast they're moving themselves, they get the same answer. And that's very strange. That shouldn't be true if the world worked the way we intuitively think it does. Let me give you an example. Suppose I'm standing on a platform and I throw a ball towards you at, let's say, 20 miles per hour. And suppose you're standing on a train that's moving at 30 miles per hour. From your perspective on the train, how fast is the ball approaching you? Well, we just add them together, right? 20 plus 30 gives us 50 miles per hour. That's what we call Galilean relativity. It seems obvious. The speeds add up. But light doesn't work that way. And this is the crucial point. If I'm standing on a platform and I shine a flashlight toward you, and you're on a train moving at, say, 100,000 miles per second, which is impossible, but let's pretend, the light from my flashlight will still reach you at exactly 186,000 miles per second. Not 186,000 plus 100,000, just 186,000. Every observer everywhere measures the same speed of light. Einstein recognized this as one of the most fundamental facts about nature. And he built the entire theory of special relativity on this one observation. Now, why is this so important? Why should we care if light travels at a constant speed? Well, because it tells us something absolutely revolutionary about the structure of reality itself. You see, the speed of light isn't really about light at all. It's about space and time. It's about how these two things are woven together and what we mean by now. Let me think about this carefully. In our everyday experience, we think of space and time as completely separate things. Space is where things are, and time is when things happen, and they don't have anything to do with each other. When I say it's noon right now, I think that's something that's true everywhere in the universe at the same moment. But the constant speed of light tells us that this intuition is wrong, dead wrong. Here's why. Imagine you're on a spaceship traveling at half the speed of light, which is impossible, but stay with me. And you want to know what time it is at a distant point in space. How would you find out? You'd send a light signal. The signal travels at the speed of light, of course. It gets there and bounces back. And from the time it takes for that signal to make the round trip, you calculate the time. But here's the thing. The time you calculate depends on how fast you're moving. Two observers moving at different velocities will disagree about what time it is at that distant location. Now, what does this mean? It means that now is not a universal thing. There's no such thing as a moment that's happening everywhere at once, independent of how you're moving. The concept of now is tied to your motion through space. It's relative. This is what physicists call the relativity of simultaneity, and it's one of the strangest and most wonderful consequences of the constant speed of light. But let's dig deeper. Why is the speed of light constant? Why is it always the same no matter who measures it? Well, if you think about it from the perspective of the speed of light, the answer becomes clear. A photon, a particle of light, has no mass. And if you've got no mass, you can't stay still. You have to move at the maximum possible speed, which is the speed of light. It's not that the light chooses to go at this speed. It's that for a massless particle, this speed is inevitable. But here's where it gets really interesting. For a massless particle traveling at the speed of light, something extraordinary happens. Time stops. From the perspective of the photon, no time passes at all. No matter how far it travels across the universe, from its own point of view, the journey is instantaneous. A photon born in the heart of a star and traveling to your eye takes zero time. It's eternal, in a sense. It's always being emitted and always arriving simultaneously. Now, we can't experience that ourselves because we have mass. We can never reach the speed of light, but this tells us something profound about reality. It tells us that the speed of light is the speed limit of causality. It's the speed at which cause and effect can propagate. It's the speed at which information can travel. And this speed, this cosmic speed limit, is what stitches space and time together into a single fabric that we call space-time. Let me think about this with another way of looking at it. Imagine I've got a clock, a very simple clock, just two mirrors with a light beam bouncing between them. Each time the light bounces, that's one tick of the clock. Now, when I'm holding this clock in my hand at rest, the light beam travels some distance between the mirrors and makes a tick. Very simple. But now imagine I'm moving this clock past you at a very high speed. From your perspective, the light beam has to travel further to go from one mirror to the other because the mirrors are moving. But here's the key point. The speed of light is the same in your reference frame as it was in mine. So if the light has to travel further at the same speed, it takes longer. The clock ticks more slowly from your perspective. This is time dilation, and it's not an illusion. It's real. Time actually does run at different rates for objects moving at different velocities. This was demonstrated experimentally, you know. They took atomic clocks, put them on airplanes, flew them around the world at different speeds, and when they came back down and compared them to clocks that had stayed on the ground, the traveling clocks had lost time. Not much. We're talking fractions of a second, but measurably less time had passed. And the amount of time lost agreed exactly with Einstein's prediction based on special relativity. Now, what does this have to do with the present moment, with now? Everything. You see, the fact that time runs at different rates depending on your velocity means that there is no absolute present moment. There is no universal now that's the same for everybody. The present moment, the boundary between the past and the future, is different for you and me if we're moving at different velocities. I'll give you a concrete example. Imagine you're on a spaceship moving away from Earth at some significant fraction of the speed of light. And imagine that right now, from your perspective, a certain event is happening on Earth. Maybe it's the birth of a child. You think of it as happening right now. But from the perspective of someone on Earth, that event might have already happened, or it might not have happened yet. And both perspectives are equally valid. There's no fact of the matter about whether that event is happening right now or not. It's not that we don't know. It's that the question itself doesn't have a unique answer when different observers are moving at different speeds. This is really hard for people to accept because we have this deep intuition that there's a present moment that's real and objective, independent of anyone's perspective. But the physics tells us that's wrong. The present moment is observer dependent. It's subjective in a sense, though it's determined by objective physical laws. Your now is not my now if we're moving relative to each other. But here's the most beautiful part of all this. The thing that holds all of this together, the thing that makes it consistent and sensible, is the speed of light. The speed of light is the ultimate speed at which information can travel. It's the speed at which one part of the universe can influence another. It's the speed that connects different observers' concepts of now into a coherent whole. It's the speed that's the same for all observers, regardless of their motion. In a very real sense, the speed of light is the speed of now. It's the rate at which the boundary between past and future propagates through the universe. It's the rate at which one observer's present moment extends into another observer's future. When you see the sun in the sky, and you're seeing it as it was 8 minutes ago, because that's how long light takes to travel from the sun to Earth, you're literally seeing the past. Light carries information about events that have already occurred. Think about what this means for the entire universe. Everything you've ever seen, everything you know about anything that's far away from you, you know about it through light that has traveled to your eyes. The furthest galaxies we can see are billions of light years away, which means we're seeing them as they were billions of years ago. We're looking back in time. And the events we're observing are no longer now for us. They're in our past because the light that brings us the information about them was traveling at the speed of light. And light takes time to get here. This is where it gets truly profound. In a universe without a speed limit, in a universe where information could travel infinitely fast, there would be such a thing as an absolute present moment. Everyone, everywhere, could know what was happening everywhere else simultaneously. There could be a universal now. But in our universe, where nothing travels faster than light, there is no universal now. The present moment is woven into the fabric of each observer's motion through space. Your now is a surface that cuts through space-time at an angle determined by how fast you're moving. And this isn't just mathematical abstraction. This has real consequences. There's a phenomenon in quantum mechanics, for instance, where particles can be entangled, where they have a strange correlation between their properties no matter how far apart they are. Some people used to think this meant information was traveling faster than light instantaneously from one particle to another, but it's not. And the reason is precisely because of what we're talking about. The speed of light is the limit. Information cannot travel faster than light. The correlations in entangled particles are preserved in such a way that no faster than light signaling is possible. Let me also mention something about gravity and time. Einstein showed us that gravity is not just a force pulling things down, it's actually a curvature of space-time. And what determines how space-time is curved? It's the presence of mass and energy. Massive objects curve the space-time around them, and this curvature is what we experience as gravity. But here's the thing. This curvature affects how time runs. Time runs faster in some places and slower in others, depending on how curved the space-time is. And the speed of light, interestingly, is what connects all of this together. At the surface of a black hole, for instance, time nearly stops relative to what it is far away. And right at the event horizon, the point of no return, time effectively stops completely. This is why a black hole is black. Not because light is being pulled in and crushed, but because time becomes so warped that light can't escape. From the perspective of light itself, which experiences no time, it's trying to climb out of a gravity well where the slope is infinite. It's a beautiful thing, really. Now, I want to bring this back to what I said at the beginning. The speed of light is the speed of now. What I mean is that the present moment, your experience of now, is propagated through the universe at the speed of light. When you make a decision and act on it, the effects of your action don't ripple through space instantaneously. They propagate outward at the speed of light, no faster. This is why causality is preserved. This is why the past remains the past and the future remains the future, despite the fact that now is not an absolute concept. The reason the speed of light is what it is, about 186,000 miles per second, is, in a deep sense, tied to the structure of the universe itself. It emerges from the properties of space and time and the particles that move through them. There's a calculation you can do. It's beautiful, really, where you start with just the properties of electricity and magnetism, and out pops the speed of light. Maxwell did this in the 1860s, before Einstein was even born. The speed of light is written into the fabric of reality. I think what makes this so remarkable is that by understanding the speed of light, we're not just understanding how fast light moves. We're understanding the fundamental nature of reality itself. We're understanding that space and time are not separate entities, but aspects of a single unified thing, space-time. We're understanding that cause and effect must propagate at a finite speed, which means distant events in space-time are not correlated unless light could have traveled between them. We're understanding what now really means, not an absolute universal concept, but something that depends on your motion through space. And this is where science reaches something quite profound. We started with a simple question: how fast does light travel? And it led us to realize that the speed of light is intimately connected to the very structure of reality, to the nature of causality, to what we mean by time itself. The speed of light is the speed at which the present moment propagates through the universe. It's the speed of now, an understanding that has been one of the greatest insights in human history. You know, Einstein never felt entirely satisfied with the way he presented these ideas. He said he wished he could explain relativity in a way that was so simple and clear that any intelligent person could understand it without mathematics. He came close. But the fact is, when you really understand what's going on, when you see how the constancy of the speed of light forces us to reconsider what we mean by space, time, simultaneity, and now, it becomes not just clear, but beautiful. It's one of the great triumphs of human thought, and it's based on one simple observation. The speed of light is always the same, no matter who measures it. Everything else follows from that. And that, in the end, is the Feynman reality check. We take an observation, something we can verify experimentally, and we follow it to its logical conclusions no matter where it leads, no matter how strange it seems. We don't let our intuitions and our preconceptions stop us from seeing how nature really works. And when we do that, we discover something far more wonderful than what we imagined. The speed of light is the speed of now, because it's the speed at which reality unfolds, the speed at which the future becomes the present and the present becomes the past. And in understanding that, we understand something fundamental about who we are and where we fit in this universe.